Hello and welcome to this lecture where we'll discuss the stability and frequency response of feedback amplifiers. Our objectives for this lecture are the following: to determine the conditions for instability or stability of feedback amplifiers, to plot the magnitude and phase response of feedback amplifiers. Specifically, we will look not only at the plot of the closed loop gain, but also at the forward and loop gains and see how they are related to the closed loop gain through these plots. Lastly, to identify if a feedback amplifier will be unstable based on the loop gain Bode plots. We have seen from the previous lecture that feedback affects the pole locations. Now let's look at how this is related to stability. The poles, which are the solutions to the characteristic equation of a transfer function, determine the form of the characteristic response of a system. Each pole at some s is equal to sigma naught plus j omega naught in the S domain contributes some term of the form k times e raised to sigma naught times j omega naught times t in the characteristic response. Here we observe that if sigma is less than 0, meaning the pole is at the left half plane of the complex S domain, then the pole will contribute an exponentially decaying term, which should lead to a stable response if all other poles are also in the left half plane. However, if sigma naught is greater than 0, meaning the pole is at the right half plane, then the term it contributes will exponentially grow in time and thus produces an unstable response. It must be clear that instability is characterized by the existence of at least one pole in the right half plane. If three poles are at the left half plane but one pole is at the right half plane, then the system is still considered or is still unstable. To help us visualize better, a system with a pole along the real axis in the left half plane, or LHP, will contribute an exponentially decaying term in the time domain response. A complex conjugate pole at the left half plane will contribute an oscillatory term, but with an exponentially decaying envelope. A complex conjugate pole at the right half plane will contribute an oscillatory term with an exponentially growing envelope, such an unbounded behavior is considered unstable. If the pole is located along the real axis at the right half plane, the output will be exponentially increasing and is thus still considered unstable. If the complex conjugate pair has a zero real part or is lying in the j omega axis, then its response will be some sustained oscillation. Since the output is still bounded, we are considering this response still stable, although we will use the term marginally stable since the transient does not decay as well. Oscillator circuits based on feedback are designed to put the poles deliberately at this location or slightly into the right half plane. Since feedback tends to move the pole locations, then the system can become unstable. We have shown in the previous lecture how the poles move in single and two-pole systems. Based on the root locus of the two systems, it can be inferred that they will never be unstable regardless of the loop gain. However, more complex and practical systems will have more poles. In the case of a three-pole system, the two low-frequency poles will approach each other and become complex conjugate poles. However, these poles can end up being in the right half plane if the loop gain is large enough. When this happens, the system will become unstable. Looking back, the pole locations of the closed loop system are ultimately determined by its characteristic equation, which is 1 plus T of S. Thus, in studying stability, the focus is more on the loop gain and not the closed loop gain, nor the open loop gain per se. While pole zero plots of the closed loop gain can easily tell us if the system is unstable or not, a lot of the other properties of the system are not shown or hard to infer from such plots. To help us characterize the system, we make use of the frequency response, which is simply the transfer function evaluated at s is equal to j times omega. The frequency response also describes the output of a system when fed with a sustained sinusoidal input with a fixed frequency. The frequency response of a system has two components, the magnitude response and the phase response, which can be visualized and drawn quickly using Bode plot approximations. To appreciate how plotting the frequency response will help us in analyzing feedback systems, consider the sample system described. The forward gains transfer function or impulse response is given in terms of S. To get the frequency response, we simply replace S with j times omega. And note also that we have replaced P1 with omega P1 to avoid confusion with evaluating the frequency response denominator to 0 and treating that as the actual pole location in the S domain. Now let's try and plot the magnitude and phase responses individually. For the open loop, loop gain, and closed loop frequency responses, if we are to use the following values: DC open loop gain of 10,000, first pole frequency at 100 radians per second, and feedback factor of 0.1. We have just copied the given at the first line. Note that we are plotting first the magnitude response in this slide. The first thing we can plot is the open loop gain. Equation-wise, A of j omega is 10,000 over 1 plus j omega over 100, and the magnitude plot is shown on the right. The plot starts at 10,000 and remains relatively constant at lower frequencies. At this range, the j omega over 100 term is still much smaller than 1, and so the denominator is just approximately 1. The gain decreases by a factor of 10 for every decade change in frequency at frequencies much larger than the pole frequency. This is because at this region, the 1 term is already negligible, and the magnitude is inversely proportional with omega. The next thing we can plot is the loop gain, magnitude response, or T of j omega's magnitude. We just have to multiply A of j omega by F, which is 0.1. Thus, the magnitude of T of j omega starts at 1000 instead, and the whole plot is shifted down and scaled down by 0.1. It is also obvious in the plot that the open loop gain and the loop gain have the same pole frequencies at 100 radians per second. We highlight the fact that the loop gain is just a scaled version of the forward gain, or the open loop gain in this case, and in other cases we'll consider in EEE 141, where F is just a real constant. We have just reproduced the same magnitude response plot in this slide, although this time the y-axis is now in dB. Note that the DC open loop gain, A0, of 10,000 corresponds to 80 dB, while the DC loop gain of T0, which is 10,000 times 0.1 or 1,000, corresponds to 60 dB. The plot also shows the minus 20 dB per decade roll-off after the pole frequency, which is at 100 radians per second. Now, in plotting the magnitude response of feedback systems, it is also common to plot 1 over F, or the inverse of, or the reciprocal of the feedback factor. This line will be helpful since the closed loop gain is approximately 1 over F if T is very large. In our example, since F is equal to 0.1, then 1 over F is equal to 1 over 0.1. which is equal to 10, which corresponds to 20 dB. In the plot, the orange line is the 1 over f line. Now we'll show an alternative way of visualizing the loop gain. The loop gain is the green plot whose positive dB values are also highlighted. Looking at the equation for the loop gain in dB, T of j omega is simply A of j omega times f. With the properties of logarithms, the function can be separated into 20 times log of the magnitude of j omega plus 20 times log of the magnitude of f. Since we already have the 1 over f plot, we can instead rewrite the equation and see that the magnitude of the loop gain in dB is just the open loop gain in dB minus 1 over f in dB. Subtracting the two plots should result in the portion highlighted, at least for the positive part. Indeed, the two green highlighted parts are exactly the same. Thus, it can be said that the magnitude response of the loop gain, T of j omega, can be visualized using A of j omega, but with the 1 over f line as the 0 dB. This is specifically true when f is purely real or just a constant. However, if f varies with frequency, the loop gain must be visualized strictly as the difference between the A of j omega line and the 1 over f line, which may change with frequency. Let's now take a look at the closed loop magnitude response. The closed loop response has a DC gain of A naught over 1 plus T naught, which is 10,000 over 1 plus 1,000, which is 1,001. Overall, that is around 10, which corresponds to 20 dB, which again is this 1 over f value. We have also shown that for a single pole system, the closed loop gain will have a bandwidth that is 1 plus T naught times larger than the open loop bandwidth. Thus, the bandwidth of the closed loop system is at 100 radians per second, omega p1, times 1001, or roughly 100,000 radians per second. Plotting that should give us the red line shown, where the DC gain of 10 corresponds again to 20 dB, and the 20 dB per decade roll-off starts at the closed loop pole or bandwidth, which is 100 radians per second. So again, this plot shows the gain to bandwidth trade-off and how the gain is decreased and the bandwidth is increased by the same factor, which is 1 plus T naught. Highlighting the numbers, the gain decreased from 10,000 to simply 10, or from 80 dB to 20 dB. Meanwhile, the bandwidth increased from 100 radians per second to 100,000 radians per second, which is also seen in the magnitude plot. However, going from open loop to closed loop, the gain bandwidth product is maintained at 1 mega radians per second. So for the open loop gain, 10,000 times 1 100 is 1 megaradians per second. For the closed loop, 10 times 100,000 is 1 megaradians per second still. This is also evident with the same 0 dB intercept or unity gain frequency, which approximates the gain bandwidth product for a single pole system with DC gains considerably above 0 dB. Since if the system has a gain of less than 0 dB, then it will not anymore intersect 0 dB. And we want to be at this constant slope line considerably far from this arch right here. Now let's take a look at how the three plots, A of j omega and the magnitude, 1 over f, and ACL of j omega are interrelated. The closed loop gain can be written in the familiar forms, A over 1 plus t, and 1 over f times t over 1 plus t. Thus, the magnitude of the closed loop response is just when we have a fraction, is just the magnitude of the numerator over the magnitude of the denominator, although we are considering f as a purely real constant. Now let's focus first at the left portion of the plot, where the loop gain, as highlighted in green, is still positive or greater than 0 dB. So note, for the loop gain, the 0 dB is the 1 over f line. When the magnitude of t of j omega is much greater than 1 or 0 dB, then ACL, or the red one, simply follows the orange line, which is 1 over f line, which is consistent if we inspect this equation. In this case, since t of j omega is much greater than 1, then the denominator is just approximately t of j omega, and t of j omega in the numerator and the denominator will cancel, and we are left with approximately 1 over f. However, when the magnitude of t of j omega is much less than 1 or 0 dB, at the portion where the 1 over f line is now above the blue line, or the A of j omega line, then the closed loop gain, magnitude of ACL, simply now follows the blue line, or A of j omega, which is now can be easily seen with this form, where if t of j omega is much less than 1, then the denominator is simply approximately equal to 1, and therefore the closed loop gain will be approximately equal to the open loop gain. Now, when the magnitude of t of j omega is around 1, this is the part where the blue line is around the orange line, or the open loop gain is around 1 over f. The magnitude of the denominator, 1 plus t of j omega, the whole thing here, now depends on the phase of t of j omega. It is now important to note that we are concerned with the magnitude of 1 plus t of j omega, and not 1 plus the magnitude of t of j omega. So the two are different things. For example, say t of j omega is its magnitude is 1, but its phase is negative 90 degrees. Then the denominator, 1 plus t of j omega, its magnitude is square root of 2, or around 1.41. Now, this is actually the case for the plot shown, where the closed loop magnitude is the open loop gain magnitude divided by square root of 2, which means that the closed loop gain is the open loop gain minus 3 dB, which shows this minor difference here. For another example, say consider that T of j omega is still 1, its magnitude is still approximately 1, but now its phase is negative 135 degrees. So the magnitude of 1 plus T of j omega is the magnitude of 1 plus 1 angle negative 135 degrees, which should give us 0.765. Now in this case, the closed loop gain, ACL, is equal to the open loop gain divided by 0.765, which means that now the closed loop gain is slightly higher than the open loop gain since the denominator is less than 1. As a last example, if T of j omega still has a magnitude of 1, but with an angle of negative 180 degrees, or simply 180 degrees, then the denominator will be 1 minus 1, or 0. And since the denominator is 0, then the closed loop gain will approach infinity. And this is the case where if the pole is already at the imaginary axis of the S domain. So if you recall, the magnitude response or the frequency response is evaluated at S is equal to j omega, and if the pole now lies at the complex plane, then the infinite response at the exact pole locations will now appear clearly in our frequency response. Now, to highlight, the first two bullets give us an easy way to sketch the closed loop magnitude response, at least at the two extremes. If A of j omega, the blue line, is much greater than the 1 over f line, then we just need to copy the 1 over f line. However, if A of j omega, the blue line, is much less than the 1 over f line, the orange line, then we just copy the blue line, which is A of j omega. Before plotting the phase response, let's have a quick review first. Given an expression h of j omega with a positive DC gain and the pole at the left half plane, the angle of h of j omega is the sum of the angles of the terms at the numerator minus the sum of the angles of the terms at the denominator. In this case, there is only one term for both numerator and denominator. Since a0 is positive, its angle is 0. The angle of a complex number, meanwhile, is the inverse tangent of the imaginary part. In this case is omega over omega p over the real part, which is just 1. At very small frequencies, the angle approaches 0 minus tangent inverse of 0, which is simply 0. When omega approaches infinity, the overall angle is 0 minus tangent inverse of infinity, or the angle of h of j omega thus approaches negative 90 degrees. Now let's take a look at the equations that describe our example. In all cases, the DC gain is positive, and thus all plots should start at 0 degrees. The open loop and loop gain have the same pole frequencies at 100 radians per second, and the difference in the DC gain, 10,000 versus 1,000, will not matter since the angle of 10,000 and the angle of 1,000 are both 0 degrees. We also know that the angle of A of j omega and T of j omega will be exactly the same if f is just a positive constant. If f happened to be a negative constant, then they are off by 180 degrees. Each 1 plus j omega over omega p pole term will contribute a total of negative 90 degrees phase shift, with a negative 45 degree shift happening exactly at the pole frequency, and the phase change having a minus 45 degree per decade slope. This slope starts approximately at 0.1 omega p and ends at 10 times omega p. For the case of the open loop and loop gain, the transition happens from 10 to 1000. For the closed loop gain, since the pole moved to 100,000, then the shift happens from around 10K to 1 megaradians per second, and the exact minus 45 degree phase shift happens at the exact pole frequency at 100 kiloradians per second. Okay, so that ends our numeric example of magnitude and phase response plots. We will now relate the frequency response, both magnitude and phase response plots that we have drawn, to the stability of the system. In a stable feedback amplifier, the loop will attenuate all transients when the input has settled. This is consistent with the decaying transients for poles at the left half plane of the S domain. For this to happen, we have to ensure that the angle of the loop gain T is less than 180 degrees, or stays between positive 180 to negative 180 degrees, to maintain negative feedback operation. Meaning the feedback signal must not be negated or flipped before subtracting from the input signal in generating the error signal. Otherwise, if the feedback signal is negated before subtracting, then we are performing positive feedback instead of negative feedback. In a stable system, the angle of the loop gain is only allowed to be more than 180 degrees if the loop gain magnitude is already less than 1. In this case, since the feedback signal is already flipped, so the system is effectively in positive feedback, but the signal is attenuated for every pass of the loop, which allows the transient to decay and not blow up. If both of these sub-bullets are followed, then the system is stable. There is another way to characterize or categorize the stability of a system using the simplified version of the Nyquist criteria. In this test, the circuit is said to be unstable if the loop gain magnitude is greater than 1 at the frequency where the loop gain is 180 degrees, or actually also negative 180 degrees, which we will denote as omega 180 degrees. Aside from categorizing a system as stable or unstable, we would also want to have some metric on how far is our system from being unstable. For this, we normally use the metrics called phase margin and gain margin. Phase margin is the additional phase shift needed to be added to the loop gain before the system becomes unstable. It is measured at the frequency where the loop gain is unity or 0 dB. Equation-wise, Pm is equal to the angle of T at its unity gain frequency minus negative 180 degrees. This form is more convenient for us since we will be dealing with systems that tend to shift the phase downwards or clockwise. A phase margin that is greater than 0 means that the system is stable. However, this is generally true only if the loop gain and the phase crosses the 0 dB and negative 180 degrees respectively only once. In cases that either of the two is not true, then the frequency response must be inspected based on the more generic statements in the previous slide. Gain margin, on the other hand, is the amount of additional loop gain before the system becomes unstable. This is measured at the frequency where the loop gain phase shift first reaches negative 180 degrees. Defining by equation, Gm is equal to 0 dB minus loop gain in dB at its omega 180 degrees, or the frequency where the phase shift is negative 180 degrees. A Gm that is greater than 0 dB means that the system is stable. Similar to the comment on phase margin, this statement is generally true only when the gain and phase responses cross 0 dB and negative 180 degrees respectively only once. Otherwise, more careful inspection is needed. Note that it is also possible that the phase and gain margin must be measured with respect to the positive 180 degrees if the phase change tends to increase towards that direction. To aid our understanding of the definitions presented, let's consider an example with actual numbers. Determine the phase and gain margins for a feedback amplifier with a forward gain of A of S of 2000 over 1 plus S over 10 raised to 3 times 1 plus S over 10 raised to 6 and a feedback factor F of 0.5. The procedure can be outlined as follows. First, plot the open loop frequency response, A of j omega, and the 1 over F line. For the phase margin, identify the unity gain frequency of the loop gain and then identify the loop gain phase shift at that frequency before computing the phase margin. For the gain margin, identify the frequency where the phase shift is negative 180 degrees, then identify the loop gain magnitude at that frequency before computing the gain margin. Following the outlined procedure, we plot first the open loop frequency response, A of j omega. The plot starts at or with a DC gain of 2000 or 66 dB and changes with an additional negative 20 dB per decade slope for every pole, which occurs at 1 kiloradians per second and 1 megaradians per second. Note that there are 3 decades from 1K to 1 meg, so the gain goes down from 66 to 6 dB. We also note that these frequencies will be the same pole frequencies for the loop gain since F is just a constant. So again, the pole of the open loop gain is just the same poles for the loop gain. The phase will start at 0 degrees, have a minus 45 degree per decade slope from 0.1 omega p1 or 100 to 10 times omega p1 or 10,000, then go down again with a negative 45 degree per decade slope from 0.1 omega p2 or 100k to 10 times omega p2 or 10 meg. Next, we plot 1 over f. Since f is equal to 0.5, then 1 over f is 2, which corresponds to 6 dB. From these plots, we can visualize the loop gain. Again, the loop gain takes the shape of the open loop gain, but with the 1 over f line as the 0 dB when f is just a positive constant. As for the loop gain phase response, the plot is exactly the phase of the open loop gain since f is just a positive constant and the loop gain has the same poles as the open loop gain. For the phase margin, we note the frequency at which the loop gain is unity. Since we are taking the 1 over f line as 0 dB for t, then we just have to take note where the loop gain intersects 1 over f. From the plot, we can point this intersection to happen at 1 megaradians per second. Next, we note the loop gain phase at 1 megaradians per second, which is negative 135 degrees. We can then compute or measure the phase margin. PM is negative 135 degrees minus negative 180 degrees, or all in all, positive 45 degrees. The phase margin is also noted in the figure. For the gain margin, we need to take note of the frequency at which the phase of the loop gain T is negative 180 degrees. From the plot, we can easily identify that frequency as 10 megaradians per second. Then we note the loop gain at this frequency. Again, the loop gain is 0 dB. The loop gain's 0 dB is the 1 over F line. To help us in measuring, an alternate y-axis values are shown. With this, the loop gain at 10 megaradians per second is negative 40 dB instead of negative 34 dB. Thus, the gain margin is 0 dB minus negative 40 dB, or simply 40 dB as noted also in the gain plot. However, although the demonstrated procedure is relatively easy to follow, it is actually not that accurate because body plots are just approximations. For this example, different values will be obtained if calculated directly from the given expressions. If we write the expression for T of j omega from the given A of S and F, we will get that T of j omega is 1000 over 1 plus j omega over 10 raised to 3 times 1 plus j omega over 10 raised to 6. And from this equation, one can solve the following values. First, the unity gain frequency of 786 kiloradians per second and phase margin of 51.9 degrees. These values are a bit off from the values obtained from the body plot approximations. The source of the error or difference can be seen if we plot the gain and phase response without approximation, which is shown as the solid lines on the right. Note that a pole occurs exactly at 1 megaradians per second, and thus the gain at that point is actually lower by 3 dB already. And thus the intersection of the open loop gain and the 1 over F line occurs a bit to the left as highlighted. Thus, we have to measure the phase margin at this point. And since the unity gain frequency is a bit to the left, then we actually get a slightly higher or larger phase margin. Nonetheless, the body plots were still able to give decent approximations. However, for the gain margin, computing from the expressions, we will actually point that the 180-degree frequency is at infinity and the gain margin is also infinite. This is far from the approximated values of 10 megaradians per second and 40 dB. Recall that the phase is based on the inverse of the tangent function, which is just asymptotically approaching 90 degrees. Thus, the phase will actually only get to negative 180 degrees at infinity. At this point, the gain is already very low, that the gain margin is also infinity. Although not part of the original instructions, what then will we get if we plot the closed loop response? Following the guidelines we have established previously, the closed loop gain should follow 1 over F when the loop gain is very large, and on the other extreme, the closed loop gain should follow the open loop gain when the loop gain is very low, or in our plot, when the open loop gain is considerably below the 1 over F line. What then happens at the middle portion? Let's look at the exact unity gain frequency. At this point, the phase of the loop gain is negative 128 degrees, which can be computed from the presented exact phase margin in the previous slide. the denominator 1 plus t of j omega can be visualized as using vector addition in the complex plane. We can start with the constant 1, which has an angle of 0. Next, since we are considering the unity gain frequency, then t of j omega should have a magnitude of 1 with some angle, assuming that we don't know yet the phase we are considering. However, in the specific system in our example, the angle at the unity gain frequency is negative 128 degrees. We can also indicate in this figure the phase margin, or the additional angle for the denominator to be 0 and the closed loop response to approach infinity. For vector addition, we just connect the two vectors, and so 1 plus t of j omega must be this green vector. This vector is less than 1 in magnitude, and this would have been exactly 1 if the phase margin was 60 degrees, where we will end up with an equilateral triangle. Going back, since 1 plus t of j omega is less than 1 in magnitude, then the denominator is less than 1, and therefore there must be some peaking in the closed loop response at the unity gain frequency as shown. And so the closed loop response should follow this red line here. We limited our analysis in previous examples to real constant f that is encountered with the use of purely resistive feedback network. Under this assumption, what then is our quote-unquote worst case feedback factor? We can determine the answer to this question if we consider a fixed open loop response and then change only the feedback factor f. Consider the open loop response shown with 3 poles. The first pole is quite dominant, or happens way earlier than the other poles, so we can easily isolate how it causes the total of minus 90 degree phase shift However, the second and third poles are quite near each other, and thus there is a portion where the phase shift contributions overlap, and we get a middle portion with a minus 90 degree per decade slope. As a whole, having 3 poles at the left half plane, we expect that the total phase shift should approach negative 270 degrees. Now, let's take a look at 3 cases for the feedback factor f. Let f1 be less than f2, be less than f3. The lines 1 over f1, 1 over f2 to 1 over f3 decrease with higher f values. The intersection of the open loop gain to these lines should be the unity gain frequency of the loop gain for each case, where we have to take note of the phase shift and relate it to the minus 180 degree line. For the smallest f, the loop gain unity gain frequency occurs before the second pole, and we get ample phase margin of around 90 degrees. For the second case, the loop gain unity gain frequency approximately coincides with the second pole, and we get a phase margin of around 45 degrees. For the largest f, the second pole now occurs earlier, or at a lower frequency than the loop gain unity gain frequency, and we get the poorest phase margin among the 3 cases. Thus, the higher the f, or the lower 1 over f line, the poorer phase margins we will get. The worst case is the largest F possible, which in the case of a resistive divider is F is equal to 1. And thus, in our Bode plots, we can say that the worst case F will give a 1 over F line that coincides with the 0 dB line. Based also on the observations, we can say that the stability is highly dependent on the location of the second pole relative to the unity gain frequency of the loop gain T of S. The earlier the second pole, the lower the phase and gain margins. For F1, the green one, the second pole occurs after omega u, and we get a phase margin of around 90 degrees. For F3, the red one, the second pole occurs before the unity gain frequency, and we get a poorer phase margin. So to summarize what we have discussed, first, the loop gain T of S is just a scaled version of the forward gain under our assumption that F is just a purely real constant. Next, under the same assumption, the loop gain magnitude will follow the same trace as the magnitude of A of j omega, but with the 1 over F line as 0 dB. Next, the magnitude response of the closed loop gain can be traced using the table shown. If the loop gain is much greater than 1, then the loop gain follows 1 over F. If the loop gain is around 1, the closed loop response is highly dependent on the phase of the loop gain. If the loop gain is much less than 1, then the closed loop gain will follow the open loop gain. Note, however, that this is only for the magnitude, for the magnitude of the closed loop gain, and we were not able to generalize some form for the phase of the closed loop response. Next, feedback amplifiers can become unstable. When unstable, the system will produce transients that do not decay, but rather grow exponentially in time. In this case, the feedback technically becomes positive instead of negative. The stability of feedback amplifiers can be checked by looking at the pole locations at the S domain of the closed loop response, ACL of S. The poles of the open loop response move based on the amount of loop gain, and if the poles end up in the right half plane, then the system is unstable. The stability can also be checked with the use of frequency response plots of the loop gain. Take note, we are not checking the stability based on the plot of the closed loop gain. From the magnitude and phase response plots of the loop gain, the phase and gain margins must be greater than 0 for a stable system. The phase and gain margins largely depend on the forward gain's second pole frequency and the feedback factor of the system in consideration. The larger the feedback factor, the more likely that the phase and gain margins will be smaller. And that's the end of this lecture. In the next lecture, we will look at more numerical examples for practice. Thank you very much for listening.